Hi, my name is Pratik, and today we are going to look at some local search algorithms in artificial intelligence. But before we look at some local search algorithms, we must see why we need local search algorithms, because we already have algorithms such as breadth first search. The problem with breadth first search is that we have to explore every node, and it is very time consuming. So, in order to reduce this time consumption, we go with local search algorithms, in which we do not have to uh, go to every node. Instead, we usually only have single state, which means that we only have one current. So the local search algorithms are used in problems uh, which do not have strict impositions on the path we take to reach the goal, but only the goal is important. So problems like tic-tac-toe are very useful applications of local search algorithms. Also, we can use this algorithms in 8-pins problems, in which the final goal configuration is important, but not the order in which they are added. So local search algorithms, as I said, only use single current state, which means that we do not we only have the scope of single state, and we only can look at the immediate environment of the current state. Sorry. So in local search algorithms, we can see that they are not systematic, which means that we do not use any predefined notion. So as I said, that there are two main advantages of using local search algorithms, which are that they use very little memory because they obviously have single current state. And also they can find reasonable solutions in large or infinite state spaces, because we do not have to uh, travel every node. So that means that we can find reasonable solutions in infinite spaces. In addition to finding searching algorithms, in addition to finding goals, local search algorithms are also useful for providing optimization problems. As I said, that the final state is not is the important objective of the local search algorithms. So after finding the goal state, we can also use local search algorithms to find the best state in the objective function. It is very important to note that local search algorithms work in state space landscape, which we can see in this diagram. A state space landscape is nothing but a graph in which the height of the graphs represents the objective function. So the higher the peak of the graph, the closer we are to the goal state. So as we can see that there are multiple arrows pointed to the graph. So we'll look at one by one what are these. So as we can see, the global maximum, which is our goal state, our objective of the function is to reach this global maximum. And other factors are shoulder. Shoulder is nothing but a part in the graph which has a downhill on one side and uphill on another side. Similarly, we have a local maximum, which is nothing but a maximum which is closer to our current state, but is not necessarily the global maximum. We can reach local maximum easily, but it does not mean that there is no other global maximum in the whole state space. Also, we have a flat local maximum, which is nothing but like a plateau, and it has downhill on both sides. So these are the basic definitions in objective in the state landscape in which the local algorithms work. So in continuation, we can see that local search algorithms are nothing but hill climbing algorithms, as we saw in the graph. This is nothing but hill climbing. So in hill climbing, we first need to know about a simple algorithm known as generate and test algorithm. Generate and test algorithm only has 3 simple steps. The first step is, as the name suggests, generate the child nodes of the current state. The current state, I'll annotate here. The current state is the state that we are currently present in. So the first step is to generate the child nodes. So let's suppose that the node has 3 child nodes. So this is first step. The next step is to examine or test these nodes with some function. So it can be a maximizing function or any other evaluation function. So based on this function, we go to the third step, which is choosing the best node according to this function that we have applied. So these are the basic 3 steps that we can see in the generate and test algorithm. And our hill climbing is based on this generate and test algorithm. So in continuation, we have 3 basic types of hill climbing. And the first one is the most simple one, simple hill climbing. In simple hill climbing, we have as I said, based on generate and test algorithm, in which we have the current node and successor nodes. in successor node, the basic point of simple hill climbing is to go in a greedy way and not visit all the nodes. So in order to do that, we will generate the child nodes of the current node. And let us say that we have the values as 5, 6, and 7. And we have to choose the maximum in each step. So as we can see, the generated nodes have 3 different values. And in this, 7 is the maximum value. So we will obviously choose 7 as the next successor. And and we will then generate the child of this node. And we'll continue this until we either find a goal node or we do not have any more states to generate. So these are the 2 steps in which we stop the solution algorithm. So this is written here also, that we will loop this until the solution is found. That is, if the goal is found, or if there are no new operators present in the applied current state, which means that if we have this as the current state and there are no new children which we can generate, so that is another way in which we can stop the algorithm. So we can either stop if the goal is found or if there are no more children. So in continuation, let me rub this. As I said, we have these 3 criteria, 3 steps in which we can evaluate choose whether we have to see if we have to expand or not. So the first step is, in the expanded nodes, see if any of the state is goal state or not. If it is goal state, then it is good and we can stop the process. If not, we can see if there is any children that is better than the current state. So if any of the children, obviously if any of the children is closer to the goal, we will go to that state. And finally, if there is nothing, if there are no states that are better than the current state, like if we are in a current state and there are no other nodes that are closer to the goal, so we will not move further and we can say that the loop is ended. So in simple hill climbing, we have 3 main problems. So one of the problems is local maxima. Local maxima means that if we have an example, let us see an example where we can see that the current node has 3 children, 1, 2, and 3, and the values of these are 3, 4, and 5. So obviously, as I mentioned earlier, we will choose 5 as the next state. So this will become our current state. And we will then generate the children of this node. But it is not necessary that we will find the goal state from this path. In some cases, we can find the goal state by choosing 3 as our next state. So this means that 5 is the best option in the current scenario, but in the long run, it may not. It may be proven that 3 might have been the better choice. So this means that it is only the best choice in the local area, which means that it is a local maximum. So this is a problem that is occurred that we can see in simple hill climbing, and this can be overcome by using the next type of hill climbing, which is known as steepest descent hill climbing. This hill climbing method is used to overcome the problem of local maxima. So in this, it is similar up to the point where we generate the children of the node. So let us say that this is the current node, and we have generated the children node. And up to this point, it is similar to the previous simple hill climb. But we can see that the difference starts here. As we saw that in simple hill climbing, we only compare the children node with each other. So if we have 3, 4, and 5, we only compare that 3 is smaller than 4 and 4 is smaller than 5. So 5 is the greatest among these 3. So we'll choose 5. But in steepest descent hill climbing, we have to overcome local maxima because we don't know if 5 is the correct path to reach the goal or not. So in order to do that, we take a target as the goal node, and we perform this additional step of not only comparing these children node with each other, but also comparing it with the target node. And if any of these nodes are not greater than the target node, then we do not go ahead. So this allows us to overcome the problem of local maxima by not only getting stuck in the local maxima, by comparing with a greater target node, which will allow us to come out of the local maxima. So this is nothing but steepest descent hill climbing. So this allows us to get out of local maxima. But there is another problem in steepest descent. That is, if there are no nodes that are greater than a chosen target node. For suppose we have 3, 4, and 5, as you saw in the example, and we chose 6 as a target node. So we can see that none of the nodes 3, 4, and 5 are greater than 6. So this is a problem with steepest ascent, that we can now not choose any further nodes. So we have to stop the algorithm. So in order to overcome this problem, where we are forced to stop the algorithm in the middle, we sometimes use stochastic hill climbing, which is not efficient, but we use this as an alternative to steepest ascent. In this, we choose a random child, which is not only neighboring, which is not necessarily a neighbor to the current node, but in the whole state space, it can be anywhere. So we have a couple of scenarios. So let's say that we are in this area. And in this area, we can go either here or even here. So these are some of the points that we can go from here. So if the next random chosen node is lower than the current node, then we can easily ignore it and not go there, and then generate another random node. But suppose we reach here, and this is by luck we have randomly selected this. So you can see clearly that this is higher than the current node. So we can jump from here to here because we have randomly chosen it. So the stochastic hill climbing is nothing but randomly choosing another point other than the current node and seeing whether by luck we can go up. So that is nothing but stochastic hill climbing. As we have seen the 3 types of hill climbing, now we can look at the problems with hill climbing, like the disadvantages of hill climbing. We've already seen local maxima as a disadvantage, which means that we can get stuck in a local maximum, that we reach a local maximum and it may not be the global maximum. And to overcome this, we have seen that we instead of using simple hill climbing, we use stochastic hill climbing. Another disadvantage is ridges. So as we can see in this diagram, let us say that our current node is here. And we can, let us say that by going here, our cost, our function says that this is giving 5 and this is giving 3. By using greedy method, we'll always choose 5. But we can see that you choosing 5, we are going down, and by choosing 3, we are probably going to reach the goal state. So it is nothing but a local maximum. Let's say that we somehow avoided this and reached here. Now there is again this problem of whether we have to go down or go this way. We don't know beforehand going which way will take us to the goal node. So let us say again we reach this problem of local maxima. And in this graph, we are constantly reaching local maximum one after another. So this is nothing but ridges, which is a sequence of local maxima. So we have to constantly keep on overcoming this local maxima in order to reach the goal state. So the final disadvantage of hill climbing is plateaus, which is simply a region where there is nothing but plain line. So let us say that we have our current node and we have 3 children nodes, and each of the child nodes have the value 3, 3, and 3. So we can see that using greedy method will get us nowhere because all of the values are equal. So this will stop our algorithm because we do not have any no value is higher than another. So this is nothing but plateau where it can be a maximum, but we cannot go further from here. So in case it is a local maximum, it is a problem for us because if there is another goal, there is a global maximum, we will get stuck here. If it is a global maximum, then there is no problem. But if it is a local maximum, then it is a problem for us. Thank you.
Hello, my name is Jaisai Krishna from B6. Now I'm going to explain about simulated annealing search. Simulated annealing search is a combination of hill climbing and random walk search algorithms. Simulated annealing, this name comes from the metallurgical terminologies, where suppose we want to prepare a weapon, so we mold or anneal a metal to certain temperatures to provide the best metal, and it is a combination of hill climbing and random walk. So in this simulated annealing search, we combine both the advantages of hill climbing and random walk algorithms. So I want to explain it with a graph. Where this is the global maximum or the goal state, and we have a threshold line. And next, initially the algorithm is lenient and allows the bad moves, but as the graph progresses, it becomes strict. So if we consider this as the current node and we want to move to the next node, so we'll first calculate the delta E value, that is the value of the next node minus value of the current node. If the value is more and it is so if delta is greater than 0 and it is above the threshold line, we will perform the operation, means we'll set the current node to next node, or will not keep current node to next node. And if it is below the threshold line and current node, the next node value is less than the current node, that is delta is less than 0, still we'll allow the we'll keep the next node as current node. So by this, so as we can see here, the equation is e power delta E by T. So as the temperature increases, the probability function decreases. As the temperature increases, the probability function decreases, and it reaches 1, where we can reach the global maximum. So that concludes the simulated genetic search. My next topic is local beam search. So my friend explained simple hill climbing search. So this is analogous to hill climbing search, simple hill climbing search. But the variation is, now if this is the current node, that is the parent node, and if we have 4 childs, and for local beam search we have a parameter known as k, and I'm setting for this problem, I'm setting the k value as 3. So initially the algorithm starts with the parent node. If the parent node is the goal node, we'll return the solution and we'll exit the algorithm. If it is not the goal node, we'll expand that node. So we got four childs. Now, as we can see, we selected k value as 3. So for suppose the the values are 5, 4, 3, and 2. So the best 3 nodes, the k value is 3. So the best 3 nodes are 5, 4, and 3. So I'll consider these 3 nodes, and if any of these 3 nodes are goal nodes, we'll return the solution and we'll exit the algorithm. If not, again we will expand all these 3 nodes, which again may have multiple nodes. For suppose this may have 4 nodes, this may have 2 nodes, this may have a single node. Now in this next level, again we'll check whether any of this is the goal node. If it is goal node, we'll return the solution. If not, as we kept the k value as 3, we'll select the 3 best nodes, and again we'll expand it. Suppose this value has 10, this node has value 10, this has 11, and this has 12, which are the best 3 among the all nodes. So we'll expand those 3 nodes and we'll continue the search. This is the simple local beam search algorithm. A variant of local beam search algorithm is local stochastic beam search, which is analogous to stochastic hill climbing, explained by my friend Pratik. So in this, what happens is, in the simple local beam search, again we are getting the problem of local maxima, because here we expanded the node with values 5, 4, and 3, and the node with value 2 may produce the global maximum or the final outcome. But at that point, we thought that gives the output, and we expanded this, but this may give the output. So similar to stochastic hill climbing, in stochastic beam search, instead of selecting the 3 best nodes, we select the 3 random nodes, which which may be efficient or inefficient, but that is incomplete, but it may generate the goal node. Thank you. This concludes my explanation for local beam search. Now my next topic is genetic algorithms. It is a variant of stochastic beam search. To explain the genetic algorithms, I take the example of 8 pins problem. As we can see, I took four models of 8-bit strings, where this is a single model of a square of a chessboard, where each bit represents the queen value of first column, second column, and third column respectively. That is the initial population I consider. The next parameter is raw score. So the next parameter is raw score. Raw score is defined as, we can see here, for an ideal 8 pins problem, the raw score will be 28. But for this considered models, we got raw scores as 24, 23, 20, and 11 respectively. The more the raw score, the higher the fitness function. So it is directly proportional to it. So for the selection, we select the population which has high fitness function, and we will most likely eliminate the one with low fitness function. In the remaining population, we randomly select the models for selection, and in the selection process, we take we randomly choose a point where in the first one we chose the point as 3, and in the second we chose the point as 5 at the third bit and the fifth bit, and we will swap the values, which is known as crossover. And finally, we'll perform mutation, where we will randomly change a bit, which may increase or decrease the accuracy. So finally, the goal of the 8 pins problem is all the queens should be in non-attacking positions. So this genetic algorithms is based on the concept of survival of fittest. So the same thing we are doing. So we are crossing over the models which have the high fitness function to obtain a model which has more fitness function than the previous model. Thank you. That concludes my explanation with genetic algorithms.